So last we left off, we were talking about redox reactions. Do you guys remember what redox stands for? Change in oxidation state. And what is that? What was that? Not sure. Okay. So oxidation stance is defined as what? The context of chemical reactions.
Addition of oxygen. OH.
Not necessarily. It can be the addition of oxygen in the case of organic compounds. Yes. But we're going to go beyond organic compounds. Decrease of an electron. So you're saying if they're losing, if it's losing an electron, not necessarily, it doesn't have to become positive, but it could be becoming more positive, right? So the loss of an electron is oxidation. The gain of an electron is reduction. Okay, you guys remember that from last week, right? Loss of electron, oxidation, gain of electron, reduction. Okay. So, okay, so you guys have this chemical equation. What we're going to do is we're actually going to look at the oxidation state of each of the elements here, and then we're going to go through and determine which ones are going to be oxidized and which ones are going to be reduced. Okay, so if we take a look at the oxidation state based upon the rules that were given to us, we had how many rules? There's like 8 of them. Those 8 rules. I'm tattooed on your shoulder yet?
Never do that.
I would never do that. Hey, you never know what you're going to do, right?
Anything but that.
Okay, so the first one, we have aluminum solid. Aluminum solid is that going to be compound, element, ion, or aluminum solid. Element. So what is the oxidation state of an element based upon the rules? They're neutral, so they have a 0 oxidation state. Okay, so we know that that oxidation state is going to be 0. Okay, now we have a compound here. It's ammonium perchlorate. So we know that that is an ionic compound, or is that a valent compound? It is an ionic compound. Okay, so perchlorate. What would be the charge of the ClO4? -1. Okay, so based upon the rules, what should be the oxidation state of the oxygen in the perchlorate of oxygen? Yes, -2. So I'm going to put in -2 on top. Yeah, well, we'll put it up here on our main equation. So then if we have 8 of those, what has to be the oxidation state of the chlorine? I mean, so if we have 4 of those, what has to be the oxidation state of the chlorine? Positive 8?
No,
Well, because it has, remember, it has to add up to that charge.
positive 7.
So it has to be a positive 7. Chlorine has to be a plus 7 oxidation state. So if we remember, we go back to our rules, right? Take a step back. Okay, so the very first rule that says that the oxidation state of an element has to be 0, right? So elements are always going to be a 0 oxidation state, whether it's a diatomic element or whether it's a monatomic element. The next one is the oxidation number of a monoatomic ion is going to be equal to the charge of that monoatomic ion. So for instance, if we have sodium, what would be the oxidation of the sodium ion? What is the charge on sodium? Plus 1. So then what should be the oxidation state? Plus 1. Okay. Does that make sense? So if we have sulfur 2 minus, what will be the oxidation state of that? 2 minus. Minus 2. That would be our oxidation state. Okay. So the rules for hydrogen, when hydrogen is combined with a nonmetal, it's going to be a plus 1. When it's combined with a metal, it's going to be a minus 1. So in this case, what will be the oxidation state of hydrogen? What was that? It would be a negative because it's combined with the metal. Sodium, we know it's going to be a plus 1. And the rule is that it always has to add up. The oxidation state has to add up to the charge that's on that compound. So what is the charge on this compound? Did it have a negative charge over here or a positive charge? Then what is the charge? If I had sodium chloride, NaCl, what is the charge on that? It's neutral. If I have NaH, what is the charge on that? It's neutral. As long as there's no charge on it, it has no charge associated with it. So it has to add up to 0. At the end of the day, it has to add up to 0. Ionic compounds has to add up to 0. Okay? So in this case, it also is going to have to add up to 0 for its oxidation state. Okay? Overall. Okay? So, but the rule is that if you have hydrogen, hydrogen is going to be a plus 1 when it's with a nonmetal. So if I had H2O, right? We know that hydrogen is what? Each hydrogen is what? Oxidation state. Plus 1, because oxygen is a nonmetal, right? So, and that's always going to be the case for hydrogen. Hydrogen is going to be either plus 1 or minus 1 in terms of its oxidation state. Okay. So depending on who's it's paired up with. So oxygen, its oxidation state is going to be -2. So sometimes when we have peroxides, and it'll say peroxides, then the oxidation state is going to be a -1. And then very rarely we have superoxides. Superoxides, the oxidation state is going to be a -0.5. But those are really special cases. Okay. Now, if you guys go to your periodic table, Now, if you look at your periodic table, who is closer to being a noble gas? Oxygen or fluoride? Fluorine. Fluorine, right? Fluorine is how far away? Okay, so oxygen is how far away? 2. Okay, so that last rule pertains to the fact that fluorine is going to be a stronger element in terms of its pull for the electron. It's going to want it more. It's going to be more electronegative compared to oxygen. Okay, so that means that if you have fluorine and oxygen together, then fluorine is always going to be a -1, and then oxygen has to compensate for what fluorine is, because fluorine is the bully. It's the one that kind of takes over. I did talk to you guys about fluorine being, talked about acids, right? Yeah, strong acids, I guess. So fluorine is that bully that kind of makes everybody bend to its will. Okay. So then we have fluorine is always going to be a -1. All of the other halogens are always going to be a -1 unless you have something that is more electronegative than it. So for instance, oxygen is more electronegative than chlorine. So then oxygen is going to be -2, and then chlorine is going to be whatever's left over. Okay, so when we had our context of ClO4 negative, right? This is a polyatomic ion. The last rule says that the sum of the oxidation numbers of all of the atoms in a molecule, a polyatomic ion, equals the charge on the molecule for the polyatomic ion. So earlier we had NaH. At the end of the day, NaH has to equal 0. So the oxidation state of hydrogen was -1, and the oxidation state of sodium was a +1. Okay, doesn't that equal 0?
Yes.
Okay. Now, in the case of water, if each of the hydrogens are +1s, and then oxygen is what, church? What's oxygen? What is the oxidation state of oxygen? -2. So -2 plus 2 pluses is going to be what? 0. Okay. So in the case of our chlorine, the perchlorate, the chlorine here has to be a +7 because each of the oxygens was what charge? -2, right? So we got -2 times 4. It would be equal to 8, right? And they're negative, right? So -2 times 4, so -8. Okay. And then the overall charge on that polyatomic ion is a negative charge. So what does chlorine have to be for it to equal a -1? Has to be a +7. So that's how we got +7. Are you there?
Yeah.
Yeah. Okay, so let's go back to that. Okay, so let's go ahead and put those oxidation states on top. I'll put red on top of it. So we know again, aluminum was 0, chlorine is +7, oxygen is -2. Okay, what is hydrogen over here? If we have a total, break it up to NH plus, NH4 plus. What has to be the oxidation state for the hydrogens, and what has to be the oxidation states for the nitrogen?
Hydrogen is +1, and it's -3.
Okay, so in this case, nitrogen would be -3. Hydrogen is +1. Okay, we go to the other side. Now our aluminum is in a compound, right? It's in a complex. So what would be the what will be the oxidation state of each of the aluminums? And it's compound.
What's there?
Okay, what about in this compound?
The polyatomic or no?
It's an ionic compound. So what is the charge? What would be the oxidation state of the chlorine?
-1.
-1, because it is a halogen and there's no oxygen or fluorine present, so it's going to have that -1 charge. So then what would be for it to balance out to equal 0? So what would be the oxidation state of the aluminum?
+1.
Now
Plus
there are
three.
3 of them.
+3.
Plus 3. So we're saying each one is plus. We also know that this was -2 for each one. Okay, over here with water, hydrogen is +1, and oxygen 2. And then we have N2. So what would that be?
How much is A3?
Are you sure? What do we know about N2?
Do you multiply that by 2?
No. What do we know about N2? Yes. Well, yeah, we know that it's a gas because it says G next to it. That's true. What else do we know about it?
It's neutral.
It's going to be neutral. Why is it going to be neutral?
It's a covalent bond of itself.
Okay, and that's called what? There are 7 of them. Have no fear of isobeer. It's diatomic. It's a diatomic element. So since it's a diatomic element, we know that it's going to have what charge associated with it? What did you say earlier, just a second ago?
0.
It's going to have a 0 charge associated with it, because all elements are going to have a 0 charge associated. Okay, so you got to remember your diatomics. When you have an element by itself and there's multiples of it, first thing that you should think of is either a polyatomic or diatomic. Which is your polyatomic ions? Let's remember. Remember first week of class, you just dumped it out, huh? Sulfur and sulfur is 8 and phosphorus is 4 or 6. I can't remember. Okay, so we know that sulfur and phosphorus are polyatomics, and then our diatomics, we know that there are 7, and plus we also know that there's an ion that's also a diatomic, right? So what were the 7?
You said it.
Oxygen.
That's correct. Okay, now that we've got this kind of laid out, so if we take a look from one side of the equation to the other side of the equation, let's go from the aluminum. We're going from a 0 oxidation state to a +3 oxidation state. Okay, so are we losing electrons or are we gaining electrons? We're going from 0 to +3. We're losing, right? We're losing electrons. So would that be oxidation or reduction? Okay, Leo. So we know that this will be oxidation. So aluminum is being oxidized. Okay. What else? Now, if we take a look at nitrogen. Nitrogen is going from the -3 to 0.
Oxidized.
So we're going from a negative to a 0. Is it gaining? Because you have to think of it as electrons. Electrons are negatively charged. Is it getting more negative?
No.
No, it's not getting more negative. So then it is
Oxidized.
oxidized. Okay. So let's take a look at hydrogen. Hydrogen is +1 over here, and it's +1 over here. +1 to +1. Neutral, no effect. Okay. What about chlorine? Chlorine is going from a +7 to a -1.
Gain of electrons.
So it's gaining electrons. So if it's gaining electrons, it reduced. Okay, what about oxygen? It's -2 over here, and it's -2 over here. Neutral. Okay, so in this case, we have aluminum and nitrogen being oxidized. So they're going to be giving up their electrons, and then chlorine is going to be taken. They're going to be gaining, it's going to be gaining. Okay. Questions? Concerns? Catch? Okay, so this is an example of a oxidation and reduction reaction. It's also an example of a combustion. This is used for jet fuel, rocket launches. Okay. So often we will have equations that we have to solve and that we have to figure out which way things are going. So like for instance, we have, this is an example, a single replacement reaction is often a redox reaction. Okay, so if we take a look at this, we can break this up into 2 individual halves, right? We can break it up into the copper half, and we can break it up into the silver half, 2 independent equations. Okay, so if we take a look at this, first off, let's make it to a total ionic equation. Do you guys remember how to do that? So let's break it down to a total ionic equation. Cu S plus 2 Ag plus 2 NO3 minus yield Cu. What is the charge on the copper?
Plus
Plus AQ. And then we're going to have 2 NO3. Plus 2 Ag. Okay, who are our spectators? Was that Ag?
Am I crazy?
Now, it's an ion on one side and it's a solid on the other. It's a element on the other. So is that exactly the same on both sides?
No.
So you're saying nitrate?
Yeah.
Nitrate?
Yeah.
Okay. You guys agree with it?
I agree with myself.
You agree with yourself? That's the one part. First part, right? Okay. So we know that we can get rid of that, right? So at the end of the day, we're left with just copper. Solid plus 2 Ag plus AQ is going to yield Cu 2 plus 2 Ag solids. So that's going to be our total ionic equation. Okay, so let's go ahead and borrow that equation. Put this up here. Does that make it fun? Okay, so we can actually break this down into 2 half equations. One for reduction and one for oxidation. Okay, so let's just look at the copper. Copper is going from Cu, solid, to Cu, two plus. Okay, now what has to be happening to this? For it to go from Cu to Cu 2 plus.
It's losing an electron.
It is losing electrons. How many electrons is it losing?
So
So we'd represent that as,
2.
so then if we do the same thing with silver, we have 2 Ag plus now it's going from Ag plus to just Ag. So what must be happening in that case?
It's gaining an electron. Or 2 electrons.
It's gaining. Okay. Since there's 2 of them, each one is gaining an electron, right? So if we add these 2 equations together, we have an electron on both sides, so the electrons are canceled out. So our total equation, which is shown up here, right? Our total equation, our net ionic equation, which is shown up here, is just the sum of the 2 half reactions. So the first one, copper losing 2 electrons, the loss of electrons is at oxidation or reduction. Oxidation, Leo, right? Did I put a minus for copper? Yeah, it's losing 2 electrons here, right?
So for losing, should it be subtraction or?
No, it's still at
Because
addition.
it represents
Because-
the 2 electrons that left the copper.
Yes. So E represents electron, right? So if you're losing 2 electrons, that means that they're moving away from that copper, right? And so where here we have 2 electrons that are being added. So you'll never use a minus sign in the equation. It's always going to be a plus.
So
Yes,
So the arrow is representing that it's turning into that, right?
that's right.
So the arrows defining if it's yes. Okay. So, and the one for silver under, right, because it's saying +2e there, that means it's gaining the electrons in the final.
That's right. Yeah, and that would be called
Reduction.
reduction. Okay, so we know that this one is GER. Gain of electron reduction. Okay, you guys see that?
Just wanted to clarify.
Everybody got this down? Ready to move
Yeah.
forward? Yes. That's a very good, yes, very good point. So at the end of the day, for the sum for both of those equations to add up, if copper is losing 2 electrons, then the silver has to be gaining 2 electrons. And so we have to multiply the whole thing by 2. But that is a good question. So normally we work our way up to it. So we're just kind of working backwards. Okay. Everybody there? How are you guys doing so far? Good?
Yeah.
Okay. Everybody got this down?
Yeah.
Okay, good. Okay, so that experiment is just showing what happens. Now, if we're gonna balance redox reactions, we're gonna via the half reactions. So you saw how I broke it up into halves. And then, so there are a couple of rules that you want to write down. The very first rule is that redox reactions are going to take place in the nucleus medium. So it's going to either involve water, the hydroxide ion, the hydronium ion, and then you're also going to have those as potential products as well, either reactants or products. So the water and the hydroxide ion and the hydronium ions, those guys are not going to be involved in redox, right? Because if you look at it, the water is always going to be a +1, the oxygen is always going to be a -2. So those guys aren't going to be involved in that. But they're going to take place, they're going to be involved in the chemical reaction. When we first look at them, a lot of times these reactions are going to be very, very difficult to balance out. And so the best way of doing it is to break it up into half reactions. Okay, I'm going to show you an example of that. I may show you an example of that. So the steps to do that is, first thing that you want to do is write it up into your half reactions. You're going to have a redox reaction. You're going to have you're going to have an oxidation reaction and a reduction reaction. You're going to then balance out all of your elements except for the hydrogens and the oxygens. Then you're going to balance out your oxygens by adding water. Then you're going to balance out your hydrogens by adding H+. And then after you do that, you're going to balance out the charge of the whole reaction by using electrons. So at the end of the day, what you put in, you got to get out. So if your charge is a -2 in the beginning, you have to end up with a -2. Okay? And then if necessary, you'll multiply it by a coefficient. So we multiplied it by 2 just to balance it out. So those electrons for your redox reaction and your oxidation reactions, they're going to have to balance out. So you need to multiply it by a coefficient to allow them to balance out. Okay. And so you also want to make sure that you have, again, the smallest integers that you can get. And then if the redox reaction is a basic reaction or a basic medium, then you're going to use OHs to balance out your H+ on both sides of the reaction. And then you're gonna get rid of the things that appear on both sides, the spectators. And this is the one about basically. And then at the end, you're gonna just check the number of atoms and then the total charges of your reaction. So you guys want to give this shot? Because I mean, you just talked about a list, and you just talked about a list. There's a whole bunch of work on paper there. Okay, so we're gonna start off with this reaction. So the very first step is to break it up into two half reactions. So the best way of breaking it up, you see an element that's on so we have our chromium and our chromium, right? So that's going to be a reaction right there. Okay. And then we have iron 3 plus going to iron, I'm sorry, 2 plus going to iron 3 plus. That's going to be another half reaction. So those are your two half reactions. Okay. So if I have iron 2 plus going to iron 3 plus, what do I need to do to make that so it balances out in terms of charges? It's going to be losing an electron. So I'll put an electron over here. Okay. Now, in case of my chromium, so this is dichromate, the dichromate ion, and then that's going to be reduced. It's going to go to Cr3 plus. So the first part of that rule was to balance out those oxygens, or first off, balance out your element. So is my chromium balanced? How many chromiums do I have over here? And how many do I have over here? Really? I have three? I have one, right? This is just the charge right there. Okay, so I have one. So how many more do I need? So that'll be balanced. I need to put 2 here. Okay. So then I balance out my oxygens with water. So how many waters will I need to get 7 oxygens? Set 7. So 7 H2O. Okay. So, and then it says to balance out your H's with H plus. So if I put H plus on the other side, how many H pluses will I need?
14 since there are 7.
That's right. I'll need 14 H pluses. And this is under acidic condition, so I'm not going to worry about the full H's. Now, we want to look at those charges. So altogether, we have 14 plus charges here, minus 2. So that's a total of 12 charges on this side. How many charges do I have over here? So I have 12 plus charges on this side. How many charges do I have over here on my product side? Well, water is what charge? Neutral, 0, right? So there's no charges associated with that. How many 3 plus charges do I have?
6.
I have a total of 6. So that's plus 6. Okay, so how many electrons do I need to add to one of these sides so that they be equal?
6 electrons to the left side.
Okay, so I need to add 6 electrons. Okay, so then that'll make this side plus 6 as well. So both sides are equal on both sides. Okay, yeah, that look.
Makes less sense now.
It makes less sense now.
Yeah, because the plus and that, but plus means minus, so I'm confusing.
Okay, you got to get over that, right? Okay, so we know electrons are what charge?
Later.
Negative, right? So this side over here, do me a favor. Add up all of the charges on this side. Not the plus 6, just what we have. Add up all of the charges. So if I have 14 H pluses,
Yeah.
if I have 14 H pluses,
Yeah.
so what is the charge on that altogether?
14.
It's 14, so it's a positive 14, right? Okay, and then I have a minus 2.
Yeah.
So minus 2 to 14 is what?
12.
12. So I have a total of 12 charges on this side.
Yeah.
Now over here, we know that water is 0,
Yes.
okay? And then chromium is plus 3. How many of those do I have? I have 2. So that's a total of plus 6,
Yeah.
right? So how can I get it so that my plus 12 is going to be able to equal plus 6? Take away 6 or add 6 electrons,
Yeah.
right? So if I add 6 electrons, because I know 6 electrons, so then that's minus 6 plus 12, that equals 6, right?
Yes.
Does it matter which side?
It does, because the electrons have to be on the side that you're trying to.
Because it's negative, right?
That's right.
Electrons are negative.
That's right. Exactly. So in this case, we have 6 electrons added to this reaction to make this reaction happen, right? So it has to gain 6 electrons. Okay, so then, you guys mind if I erase this down? So then that first reaction, we have only 1 electron. So we have to multiply the whole thing by 6. Okay, so if I do that, then I end up with 6 Fe2 plus. And I have 6 Fe plus 6 electrons. Okay, now if I add those 2 equations, I'm going to call this equation 1 and this equation 2, and add these together. 1 1 plus 2. We have 6E minus plus 14 H plus plus CR 207 2 minus plus the 6 Fe 3 plus, and that's going to yield, sorry, 2 plus. That's going to yield R2 CR 3 plus plus 7 H2O plus 6 Fe 3 plus 6 electrons. Now, if things are on both sides of the equation, they can be canceled out. So we got 6 electrons here, and we have 6 electrons here. Right? So we cancel those out. Anything else that is on exactly the same on both sides of the equation. Okay. So in other words, those electrons that are coming from our oxidation reaction are going to be given for our reduction reaction. Okay. So oxidation, reduction, they kind of go hand in hand. Okay, you guys see that?
Yep.
That's it. Okay. So you guys, the lithium ion battery, right? The lithium ion battery is based upon this type of reaction, where one of them is going to be providing the electrons to the other, right? That's how your cell phone basically work. That's how most batteries work, based upon a redox reaction. Okay. You want to try another one? Okay. Mix this.
It's the so
Chemical reactions. It's redox reactions.
Oh. I think that's no. That's where we got the. That's where we got the. Yeah. Yeah, the right idea. Look at the road one. Slide 6. The question you had was on.
Sorry, give me 1 second. Okay, so if you go to active learning, you have Q. Start off with the second. Okay, it says complete and balance the redox reaction in an acidic solution. Be sure to include the proper phase of all species within the reaction. Okay. Second, write it all down. that's our chemical reaction that we're trying to balance. So the first step is to do what?
Separate the two reactions.
Separating into two reactions. We have redox reaction and an oxidation reaction. Okay, so we have Mn plus U. And that's going to make Mn/4 minus, so we're making it. Okay. Second reaction. Yeah. Is made. Q. Is left down. Okay. So what am I gonna do to that first reaction? First thing I should do is to balance oxygen. So how do I balance that? First off, I need to make sure that my elements are balanced. So I have one manganese over here. I have one manganese. So then how do I balance out the oxygen?
Add H2O.
And add H2O. So how many H2Os do I need to add?
4.
4. Okay, now that I've added 4 H2Os. What am I gonna do next?
I had a question.
Balance the hydrogen. Yes.
So if you have oxygen on one side, you have the H2O on the opposite side.
That's right. Because you want to balance it.
Yeah.
So one side has.
Be on the
other
opposite
side.
side.
Okay.
So
So 8.
why is it H and why is it H2O and not just oxygen?
Because it's water. So you have this, all of these reactions are occurring in aqueous solution. So in other words, you have ample amount of water, right? And so you're just basically fixing it so that you're using some of that water to make that reaction.
Okay.
Okay.
That's what you
Does that make sense? So, and it's not, you have ample amount of oxygen, you have ample amount of water. Okay. Okay, so now what is the next step? Charges. Okay, so if we look on this side here. What's the number of charges that we have over here?
2 plus.
So we have a +2 charge over here. Okay. And then over here, what do we have?
0. So it's a negative. And then a
This is
plus
a negative 1. This is
Oh yeah, plus the opposite.
big or that.
Plus 7.
+7. So we got +7 over here, +2 over here. So how can I take it? Balance out?
You have 5 electrons to the right.
Okay, we got +2, +2. Okay. Down here. Is there a bismuth balance? No. No. So then what is the next step?
That's that H2O again.
Got to add H2O.
To the right side. And 3 of them.
Yeah.
And you add the hydrogen to the left side.
Now we're doing the electron.
So we have 6 plus minus 1 plus 5. And then here we have plus 3.
Plus 6. Without- Oh no, that's 0 since it's water. So in the balance out, you add 2 electrons to the left.
Okay, so which equation is going to be reduced and which one is going to be oxidized? Red or green? Red is losing electrons or gaining electrons? Are you putting electrons into the reaction or are you taking electrons out of the reaction?
For the red, you're losing
For the
electron.
red,
Losing electron.
what's that? So the electrons are being released, right? The electrons are being lost. Okay, so this is oxidation or reduction?
Oxidation.
Oxidation. So the red is oxidation. And then the green is
Reduction.
okay, because we're putting electrons in. Gain of electrons, reduction, loss of electrons, oxidation.
Like depending on which side, if it's on the reactant or product side.
So if it's on the reactant side, you're adding, right? You're adding to the reaction. And then if it's on the product side, that means it's being lost. Okay, so what would be the next step?
Put them all together on the reactant side and product side.
But first we have to
Balance them or cross them?
balance the electrons. Right?
Oh,
So we got to balance the electrons. This one has 5 electrons. This one has 5 electrons. This one has 2 electrons. So how can I balance that?
Multiply.
Multiply by the bottom. I multiply it by what?
5.
Multiply this one by 5. And then the top one,
2.
I multiply it by 2. Plus. Plus 5 times 6.
Yeah.
Plus 5. Plus
15.
so if I add these together, electrons are going to cancel out. We have 8 water here. 15 minus 8. 7. We have 16. 30 minus 16. 14. 14 pluses. And plus. 5. 3 minus. And then minus. Plus. So let's check our charges on both sides. So we have put our charges over here. So we have 14 pluses plus 2 times 2 plus, so that's 4 plus, minus. So then that's 13 plus over here. And then on the other side, we have 2 minus plus 7 plus 2 minus plus 15 plus this. So then that's plus 13. Our charges balance out. How many hydrogens do we have? We have 14 on our reactant side. We have 14 on our product side. We have 2 manganese on our reactant side. We have 2 manganese on our product side. We have 5 bismuth on our reactant side. We have 5 bismuth on our product side. We have 15 oxygens on our reactant side. We have 7 plus 8. 7 plus 8 is 15. 15. So it balances out. Nope, that means that you screwed up so much. Yeah. At the end of the day, the charge need to match.
Let's like a double check of that.
Yep. Okay, questions? Questions? Is that a good thing or is that a bad thing? What was that? Subtracting?
Yeah.
No, it was adding. You're adding to equations, right? So it's, if you're adding, did you guys ever add equations in math? Like where you had x plus 1 equals y plus, and then here you had minus x plus 2 equals 2y 1, something like that, right? And then you add these two together, right? Those 2 equations together. So what is on one side, you just add together, right? So like in this case, we have the x minus x, right? That would be 0. So that would be 3 equals 3y plus 1. Right? Does that make sense? And then since this 1 is on both sides of the equation, right? We take this 1 and bring it over here. Right? So that would 2 equals 3y plus 3. Yeah, because you basically cancel it out. We have 30 over here, right? So in other words, I just brought this and subtracted that. That's right. Yeah. I didn't just create the number, right? That's the same thing over here with water, right? I had 8 water here, and then I just brought it to the other side of the equation, and I subtracted it by 8. That's right. So you could, yeah, so you would enter it like that, yeah. So the thing is that in chemistry, you will never have a minus. Everything's always going to be a plus, right? So it needs to go in a situation where it's a plus. If I brought this over here, that would be a negative, right? We don't want that. We want to create it. That makes sense? That's right. Yeah. Yeah, so you subtract it. It's going across. It's going across that yield sign. The yield sign is almost like our equal sign. Okay. But never use it. Perfect. Weren't you the one that wanted to use the equal sign?
Yeah, because it's a lot easier.
I'm telling you, don't do that. Okay. Okay, you guys ready for the first one? You guys go to the first one on active learning. You guys go correct.
Yeah.
Yes.
I'm going with
Okay.
Which I could learn, it should say on class, it says redox.
It
And then it's
actually
number
will.
2.
Let's see if you have it. You forgot your H class over here.
And then when you're typing it in, make sure you state it's, what is it called?
How many do you have?
State, make sure you put a state and it's
14.
if it has H plus on it or something, all that. So make sure all of it's in there, otherwise you're gonna get it wrong.
Classes on. Try to be cool. Okay, and then you must put the state. Yeah.
So, got that. That's where I wanted to work.
Okay, so let's see. You also didn't put. You need to put 2 for there.
Oh.
And then bismuth, you need to put 5 in front of it.
Right here, right?
Yeah, in front of it. Coefficient. Okay. Then you go to Mn and you put the arrow. Put it in front of that. And bismuth. So right now, what you've done, you put too many things in your equation. So that is going to that. Yeah. So you, and then you need to get rid of this. So you get that because that's on the other side.
Oh.
So then you need to get rid of that. Then you need to get rid of your 14 because that's on the wrong side of the equation. You already got your bismuth, so you need to just get rid of that magnesium. Now look at your equation. That's the bottom equation. Right? It doesn't have to be exactly the same order. It just needs to have all the components. You're missing one thing. You're missing one.
Oh, we know it. The hydrogen, I mean, the water. Oh, I forgot that.
Then if that's the case. Original. Yeah, it's not three minus. So the original equation is that minus is 3. So if you look at the very top equation, so it's here, that's not 3 minus. Then put the single minus.
I need to add Lakes for each school, right?
Four is a subset. You see how it's written? Subset, that means you have 4 oxygen. And it's like, that means that. Yeah, that means we're always- that makes sense. So, let me give you some more. Okay. So you have to work on that typing subscript in there, superscripts. Everybody got it in?
Yeah.
Are we gonna do an example where it's in a
Did you-
basic solution?
Yep, we're gonna do that right.
Aqueous solution or-
We're gonna do that right now.
Yeah, that's what I'm missing up on too. Yeah.
What was that?
Yeah, me too.
Okay.
No, you done it?
Okay. Yes.
Before you start, can you check my.
Yeah.
So we don't know, right?
Mhm.
So it's this, right? What do you think of this right?
Sure.
So let's start.
Oh.
Okay, so yeah, 2 here, so you're going 2 more. And seconds, and total 4 hydrogens. That's good. Charges. Let's see.
So the charges are here, right?
Okay, so these are, yep, 0 here, so then, yep, that looks good so far.
And for, this is what I'm having trouble with, right? Because like it has two carbon. I have to add another carbon here.
No, you need to,
Just do it by two, right?
that's right.
Okay, okay, cool.
Okay, so let's go ahead, we'll do the first one. There's a chance to. Okay. Everybody got this down? Okay, so we have permanganate reacting with oxalate to make manganese 4 oxide and carbon dioxide. Okay, so first step is to do what?
Separate.
Separate the reactions. Also know that this is a basic solution. When I say basic solution.
Yep.
So the next step would be to. Okay, so I have one in, one M in, one sides. I have 2 carbon here. So we're going to put it here.
Also, with the top one, it's the oxygen balance.
We don't have to worry about it, right? Don't care about it. We're down to water, right? So. Next step is balance the oxygens with water, right? Okay, so how am I gonna do that?
Plus 2.
2 waters? So that gives me a total of 4 oxygens, 4 oxygens. Okay, so what's my next step?
Balance hydrogens.
Was that? Hydrogens. How many hydrogens I need? Four pluses. Okay. So, next step,
Balance electrons.
balance electrons. Okay, so I have 4 minus 1 here, and I have 0 here. So I have +3. So I have +3 on that side and 0 on the other side. What do I need to do?
Add 3 electrons to the left.
Okay. Next problem. Second equation.
Ready to do.
It's balanced. Sorry,
Balance electrons again.
balance our electrons. Okay, so we have -2 here, 0 here. I'm not gonna balance the electrons.
You add 2 electrons to the right.
Okay. Okay, so we have 4, 2, 4, -2, -2. Okay. So we have 3 electrons there, 2 electrons. Yes.
I have a question. How do you know which batch of electrons? Like,
Sure. So over here, right? It was 3, it's 4 minus 1. So that's a +3, right? Over here, what is the charge right here?
0.
Well, charge is 0. So that means, what can I do to make this 0? No, I want to make this side, because the sides have to be the same. What I put in, I have to get out. That's including charges. Right now, I have a plus charge over here. I have a 3 plus charge over here. Overall, the overall thing is 3 plus. So I have to add 3 electrons to balance it out. So it'd be 0, because this side is 0. Okay? Does that make sense? Okay. So I always have to balance out my charges as well as everything else. Okay. So here, the charge is -2, right? So I have a -2 charge on this side. I have a 0 charge on this side. So how can I make it even? By adding electrons. Yes.
Oxygen is on the second. H2 is on top.
We didn't have to because it already balanced it out. Okay. Because we had 2 carbons, 4 oxygens, 2 carbons, 4 oxygens.
So we're only
So you're always going to add electrons. Yes. Somebody's going to be getting electrons, somebody's going to be giving electrons, right? Because if you look at this first equation here, right, we're putting in electrons, so we're adding electrons. This equation, we're actually removing them. Again, this is what we are, but by the reaction.
That one's oxidized, the bottom one, and top one's reduced.
Okay, this one, yes, the top one will be reduced and the bottom one will be oxidized. Yes.
So, following all that, right, I submitted it, but I said you had to do OH or something.
Because you're not finished.
Yes.
We're working on it, right?
Okay, okay,
Because it's under basic conditions, that's the last step. We'll get to that.
okay.
Okay, so if I wanted to balance this out, what am I gonna do?
You have to multiply the bottom by 3 and the top by 2 to balance the electrons.
Okay. By 2. And then I need to multiply this by Because your electrons have to balance out, they have to be
Oh,
exactly
so
the same.
So if you have those twos out there and you have three up there, you can just basically. That makes sense.
So we have 6 electrons plus 8 H pluses plus 2 manganese yields 2 manganese 4 oxides plus 4 4 2 minus oxalate. Six carbon dioxide. Okay, so pluses plus 2 minus minus plus 6. Okay, so the last part is we have to get rid of the H pluses by adding hydroxides. So we have 8 H pluses, so we're going to add 8 H minus. So because it's under basic conditions, that means that we want to have excess of OH, which is a base, right? So if you read the question, it says basic conditions, right? So that means that we're going to add the same amount of OHs to both sides of the equation that we have of our H pluses. Because H plus makes it acidic. If we have extra H plus, it's going to be acidic. If we have extra OHs, it's going to be basic. So we're going to add OHs to both sides of the equation. To make it more basic.
Basic condition to add the same amount of
OH on both sides that you have H pluses. Okay, so because we know that H plus O H minus, that's going to equal H. Okay, so this is going to make water. So we have 8 H2Os plus 2 manganese oxide, permanganate plus B Oxidate. Oxidate. Okay, so I have 4 waters here, and I have 8 waters here. So I could just subtract those 4 from over here. Okay, so try plugging in that. It works. Spot right.
I was surprised you heard me from like way over there. But
I have really good ears. I just pretend that.
are we gonna do?
Yeah. You're getting the notes down, right? Start thinking. Number 3, basic course.
I didn't check.
Oh. Yeah. So let's take a 10-minute, say 15-minute break. So let's- no, don't push your luck. So 15 minutes, 15-minute break. We'll be back here at 15. Go to Mesa, get a snack, replenish your brain cells, and then we'll come back and do number 3, the third one.
Oh, I didn't notice that. So what do you- Yeah, swap it out from H2O.
All right. Do the smallest.
Basically. Yeah. Is that 3C? Yeah, okay, I got that. His C doesn't look good, C. That's it. Yeah, I got you. Liquid, yes, I'm looking at it.
Hey, Juan. You ready for that project or what? For which one? Oh. It's supposed to be due this Thursday? Bro? And then you don't have that one guy done for either, huh? So what do you think? Me neither. That same day, remember I came in like 10 minutes left in class? So I don't know what the fuck going on.
All I know is second catapult. Like, I don't know what
Catapult? For real?
yeah, we have to make catapult. Isn't symbol or Thursday.
What do you have in this class? What do you have in this class? It's a 1 unit class. Yeah.
Oh,
The what?
it's like 80. First.
Oh. Fuck, you might be the lucky. We need that to pass.
Okay. Third one's the charm, right? Yes. About this one. Okay. Yeah.
It was at Vail. So.
Probably be your mother. My mom's a zombie. Well, aren't you? We got to pay on my phone constantly. Your dad cracks your car, I'm not surprised.
No, we're going to play board game room.
You're better be in school. Go Lewis against my mom pulled me aside. I would speak up and give the place a That's it. Like this. I feel like he came and like, holy. I know who does have game and my mom. He said, "No, I think he said, you can't do those jokes."
Okay.
Find out.
Are you guys ready?
This isn't.
Okay, so we are 2, 7. Plus. That's okay. Plus. Plus. Okay, step 1. Separate the reaction. And then what's next? There's something with water.
Balance both sides.
You want to balance both sides. Okay,
Now we add water.
now we have time.
Go to 7H2O.
Okay.
Balance the hydrogen on the other side. That'll be a 14H.
Next. Else. Next.
Now we go up to the electrons.
The electrons.
Electrons. So I have 12 here, and I have 3 here, or 6 here. Okay.
Now we balance them on the bottom reaction.
Okay.
We have a 0 on that side, correct?
0 here.
And then 2 on the other side.
Okay. So then
We had 2 electrons on the right.
Okay.
Now we have to even out the electrons. So since we have a multiple of 6, we can just multiply the bottom by 3. Now we cancel them out. Huh? Linear? We just want the electrons to be the same. So since we have an even multitude of 6, we don't have to multiply both sides by each number.
Okay.
Okay, what's next?
It's the new stuff.
What's that? Okay, what's next?
I want to make sure the electrons are balanced.
Make sure my electrons are balanced. There should be one thing that should be.
Balance them out.
And water on both sides. So
Question. Maybe I forgot to bring down the 3 on the mercury when you distributed the 3.
yeah. Three mercuries, 2 chromiums, 7, 14 oxygens, 14 charges. Yeah, -2 here. 6, 12, 14 negatives. -2 on this side. -2 on that side. Questions? Okay, so we got a bin. Importantly, got to copy it off the board.
That's fine. Actually,
Okay, go ahead, try.
Thank you.
You're welcome. Okay, everybody got it? Just testing all those skills, huh?
this is my.
So I'll leave those other ones for you guys to do here. So we're gonna move forward a little bit. Get you guys to the point where we can do the lab that you guys have, lab number.
I guess the order doesn't matter. I guess the order doesn't matter.
The order doesn't matter, it shouldn't matter.
It's not even my thing, it's all form.
No, the form can make it the phase that you're in. It's incorrect. H2O is a liquid,
Yeah, and I put the liquids in.
and then you get the mercury as a liquid.
Yeah. It's saying that. How they, which ones is wrong? I'm sure why they're wrong.
Yeah. Why there's a liquid.
Yeah.
Oh, man.
Oh. Yes,
Out of
I'm
that
just-
one.
What do you think? Liquid first, yeah.
Oh, yeah.
Okay, so. So you guys already know how to do this. You guys actually done harder ones already, so we'll just move forward. And then we'll start on reaction stoichiometry. Okay, so stoichiometry is just basically using those coefficients, right? Because we are basing everything in a chemical reaction is based upon quantity, right? Okay, so it's based upon quantity. It's not based upon mass, it's based upon quantity. Because it's based upon quantity, we're always going to be comparing those quantities relative to each other. So for instance, how many of you guys make pancakes? Good, okay, that's good. Everybody's made pancakes. Anybody not make pancakes? Okay, good. So if we make pancakes, here's our pancake recipe. One cup of mix will make plus 3/4 of milk plus 1 egg will make 8 pancakes. Okay, so if I know that 1 cup of mix makes 8 pancakes essentially, right? It's a 1-to-8 ratio. If I had 34 people or 36 people coming over, 40 people. We have 40 people coming over. So then how many cups of mix am I going to need? 5. How many eggs am I going to need? 5. So we do this all the time in chemistry, in cooking, right? So we use chemistry for cooking all the time. It's been a rough weekend, you know. I just got through cooking this morning, that's what it is. So we know that we can scale up, right? So if we know that we have a whole bunch of people coming over, we can always scale up. We also know that if we need to, we can actually scale down as well too, right? So let's say you want to make a cake, but you don't want to eat a full cake, right? You know that there are about 3 eggs in a cake, right? If I divide it by 1/3, if I divide all my ingredients by 1/3, then technically I can make 1/3 of a cake, which I would probably eat by myself, right? So the thing is that we can sit there and do that based upon quantity. At no point did I say weigh out 5 pounds of mix, or, you know, it's all based upon quantity. Okay, so when we think about chemical reactions, it's going to be based on about quantity, and we can sit there and determine how much we're going to need of one thing if we have something else. Okay, so if we have 1 cup of mix, we know we can only make at most how many pancakes? 8, and that's if we have 1 egg and 3/4 milk. What if I had a half an egg?
It wouldn't add up to the same.
What was that?
It wouldn't add up to the same amount of pancakes,
How many pancakes could I make with a half an egg?
or 4 most.
4, right? So I can use that ratio to sit there and determine how much I can actually make. Does that make sense? Okay, so that's all stoichiometry is using that ratio. The fact that I know that there's a 1-to-8 ratio between milk, not milk, eggs and pancakes, or cups of mix and pancakes. Okay, so this is just basically showing me that. So if I wanted to start off with 24 pancakes, I divide it by that ratio, 1 egg to 8 pancakes, and then I get the number of eggs that I'll need for that recipe. Okay. Question, concerns? Yeah. Now the key is that we need to know that it is the stoichiometric factor is going to be dependent on the coefficients. Okay. So we need to make sure that our chemical equation is balanced. If our chemical equation isn't balanced, then it defeats the purpose. Right? So we need to make sure our chemical equation is balanced first before we can do anything else. Right? Okay. So here's an example. If I have nitrogen gas and hydrogen gas yields ammonia. Okay? So the first thing that I would do is balance that chemical equation. Once I have that chemical equation balanced, I know that there's a 2-to-3 ratio of hydrogen to ammonia. So I can sit there and use that long as I'm using quantities for any form, right? I could talk about molecules, right? So I know that it will take 3 molecules of hydrogen to make 2 molecules of ammonia. I could be talking about dozens. I know that it's going to take me 2 dozen of ammonia, or 2 dozen of ammonia is going to require 3 dozen of hydrogen. Or I could be talking about moles, right? So any form of quantity I can actually use in this regard. Okay, long as I know that relationship. Does that make sense?
Yeah.
Okay, so an example is how many moles of iodine are required to react with 0.429 moles of aluminum, according to the following equation. Okay. Al2 plus 3 iodine yields aluminum iodide. Okay. 2 aluminum iodide. So in this case, we're given the number of moles. Our given is the number of moles of aluminum. So we're always going to be starting with our given. We're going to use that mole to mole ratio or the stoichiometric factor, right? We know that the ratio, look here, it's meant to hit annotate. If we look here, we know that the ratio of aluminum to iodide is a 2:3 ratio. So we want to get rid of the moles of aluminum. So we're going to put that on the bottom. So that's a 2 moles to 3 moles of iodine. Okay, and then that's going to allow me to calculate how much iodine I'm going to need to react with the reaction. Okay, simple. Now, if I'm given mass, I'd have to go through one step further. I have to convert to moles. So if I'm given mass, I'm going to have to convert to moles. Again, I need to make sure that my chemical equation is balanced. Is it balanced? Okay. So we have a balanced chemical equation. We're going to start off with what's given. We're given 16 grams of antacid milk of magnesium, which is magnesium hydroxide. Okay, so I have 16 grams of magnesium hydroxide. So how can I convert this to moles? How do I go from grams to moles? Molar mass. So what is the molar mass of milk of magnesia? Magnesium. Said 24 point. Okay. And then oxygen, we have two of them. 32. And then we have 2 hydrogens. So we have that together.
It's approximately 58.3197.
Oxygen and hydrogens?
Yes. 2 oxygens, 2 hydrogens. Okay. So grams going to go on top or on bottom?
But
Mole. Okay, so then that's gonna give me my moles of the milk of magnesia.
That's with 0.2744.
You said 0.2744. Okay, but what is it that we actually want?
That's the sodium.
We're looking for the mass of sodium.
Hydroxide.
So I could just keep going, right? Since that, I know that's moles of milk of magnesia. So what is the relationship between the milk of magnesia and sodium hydroxide based upon the chemical equation? It's a 1:2 ratio. So I know that if I have 1 mole of milk of magnesia, I'm gonna make 2 moles, or I'm gonna need 2 moles of hydroxide to make that. And if I remember correctly, we're looking for the mass, right? So I don't want to leave it as moles now. I want to convert that to mass. So how can I convert that to mass? Molar mass. So what is the molar mass of sodium hydroxide? Na is 3. And then we have OH. That's 16 plus 1. It's about 40 grams per mole. Okay, so now I want to get rid of moles. So am I going to have moles on the bottom or moles on top? 1 mole on the bottom. And then I'm going to have my 40 grams. Okay, so we multiply across the top and then you divide it by the stuff at the bottom. And was that 22 grams?
Second,
Yeah.
when it comes to the relationship, is it more or less looking at the coefficients in front of them?
That's right. So when we talk about the stoichiometric vectors, it is the coefficients. That's all you're looking for. Questions? Concerns? Cash? Kool-Aid? Yeah. Can I go ahead and erase? Has everybody got it? Good? Yes, yes. General consensus is yes.
Give me 2 more.
Okay,
Yeah, good stuff.
good to go. Don't fall asleep. It's the meat. This is the meat. Okay, so if we've talked about density. You guys are familiar with density. What are the units of density?
Mass over volume, specifically grams over cubic centimeters.
Okay, so if we're given density, right, we're given volume, then we can calculate its mass, right? And then from the mass, we can use the molar mass to calculate the number of moles. You guys see this? Nice little table here. Okay. If we're given volume, we can do the same thing if we have molarity, right? Because we know that molarity is what units? Molarity.
Moles over liter.
It's moles over liters. That's right. Molarity is moles over liters. So then that's going to give you my number of moles. If the volume multiplied by the molarity. If I'm given number of particles, I can use Avogadro's numbers to get me to the moles. Now, if you notice, moles is our gateway, right? Moles is our gateway drug. That gets us to everything. So if you're given grams, you can get to moles. If you're given volume, you can get to moles. If you're given quantity, you can get to moles. Okay. Does that make sense?
Yeah.
And then we can use the stoichiometric factor because we know that that is based upon quantity or it's based upon moles. Okay? Don't fall asleep.
It's not you. That's me.
I know it's not me because I'm not. Okay. So we're gonna stop here, and then this allows you guys to start working on the stoichiometric lab, which is a dry lab. And then on Wednesday, we're gonna be doing an acid and base lab. So I actually gave you this sheet as well. Okay, so this is kind of like that little figure that I showed you, although I think my figure is better than the sheet. Also because there's 2 typos. One of the typos is up here where it says pH.
Oh, I see.
You guys see that? Okay. So you see where it says the -10 log. So really that should be 10 to the negative pH. So that negative should not be there, it should be actually in the exponent. If you take a look at the sheet here, it says up top, it says -10 to the POH power. That's not right. It should say 10 to the negative pH or POH. And then the same thing with the pH as well. There's 2 types. So where it says, you see where it says pH, it should say the same thing, only thing it should say 10 to the negative pH instead of POH. Okay. And so, and then how to calculate the pH, it should be, it says POH is equal to log of the acid normality, pH. Okay, questions? Okay, so what we'll do is have you guys work on this for, give you guys 30 minutes to work on your lab. And give you the bare bones, right? And now that you have the bare bones and you guys are familiar with molarity, you're familiar with density, and then kind of have this little cheat sheet to help you with concentrations of acids. You guys should be able to get most of it. Yeah. So I'll give you guys about 30 minutes and then we'll call it a day. Play doctor. What did you say?
I think that's what they said.
I thought play doctor. And I said, what was
No,
it?
no, 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 no.
Balance, oh yeah, so we need to write down the chemical equation, yes. Okay, I thought you said play doctor, I'm like, okay.
Sure. We're about like those.
Okay, so let's go ahead and write down chemical equations. So what would be the chemical formula for titanium oxide?
And for three moles, so you get one
What was that?
mole.
It said something about play darkness again.
Then it's
Titanium oxide. So what is the chemical formula?
TO.
O2,
TI. Sorry.
TiO2.
I'll write it down.
Okay. Okay. And then they also tell us that
There.
we have titanium chloride. So what would be the chemical formula for titanium chloride?
Divide this first.
TiCl4. And then it's going to react with excess amount of oxygen. What is the chemical formula for oxygen? O2.
And that's how many grams of gallium chloride you get.
Okay, so then what would be the other product that we would be getting? Just
Really
Cl?
complicated it. Yeah, 2.6 liters. You got the ratio right. You got it upside down. This is the right thing to tell me. You want to cancel it.
What do we know about Cl? You guys told me earlier.
For 1 liter.
What was that? What do we know about chlorine? What do we know about chlorine? Oh, is it?
For every.
Okay, so then how should it be written?
You're getting 1 liter of gallium chloride because your limiter is this chloride. So you need 1 mole.
So what type of reaction is this?
1 mole gallium chloride.
Can we go over the different types of reactions?
I think you mentioned combustion.
Did I mention double replacement, single replacement? I did, didn't I mention? I said single replacement is replacing the old girlfriend for the new girlfriend. Right? So this one is replacing the old boyfriend for the new boyfriend, right? Because non-metal be replacing a non-metal, right?
One KCl because HCl is equal.
Okay.
Now you
So
want
this is a single replacement reaction.
So you put 1 mole there, plus the total weight. of
Okay, is it
one
balanced?
molecule.
Yes,
Sure.
I won't bet money.
I have cash money in here, so
Hey, we could get one to-
Hey, how do you get
I'll match it.
I have $6, $8 in there.
These are better.
When you say come on, I know I'm gonna lose, but I'm gonna
So
be
that's
ready.
just.
You're willing to bet your $8, then get $8.
You're gonna bet.
So the last one is.
That it's already down? What? That it's already down?
See, I know it's wrong because he said he.
Questions
was-
still
Let me look at, no, it's not.
Because you have to chlorine over here and then over there.
Okay.
So you need a 2 in front of the chlorine, yes, that makes sense. Now, okay. Now I'm not. I
It's
lost,
too late now.
I lost money, but. I still, I don't know, I'll buy you a top.
Okay. Okay, so now that we have a balanced chemical equation, right? Everything's balanced, everything's good to go, right? So we have a balanced chemical equation. So then now we could go into the question. And it says, how many kilograms of titanium oxide can be produced from
Do you
reacting
want to use the total?
5.60 kilograms of titanium chloride? Okay, the oxygen is in excess, right? So we don't have to worry about that. We just need to worry about how much we can actually produce. We have as much
And then you
oxygen as
don't,
we can
you
possibly
don't
need.
times it by 2 because
So then we start off with our given.
one
What's our
molecule,
given?
one molecule.
How many kilograms? 5.6 of
So I just.
titanium chloride.
5.6 kilograms.
So this is ventilators. So that's the units.
Okay.
CL,
So
moles, JCL.
what do we know about, and we have what, titanium
So 2 grams.
and chloride, right?
Titanium
Titanium chloride.
1.44
So we have,
divided by 3
is it kilograms mass?
times.
Kilograms is not mass.
So it is not for like really grams.
It's not in grams.
Yeah.
Right. Okay, so let me tell you a little secret, right?
1,000 grams is 1 kilogram, right?
One kilogram is high.
Yes. So if we wanted to, we can convert it. But we don't need to, right? And I'll show you why we don't need to.
Gives the option.
So, but if I was worried about it's, how would I convert from grams? If we had grams, how would I convert from grams to, if we had grams, how would I convert from grams to moles? I'll use the molar mass. So what is the molar mass of titanium chloride?
So we're going after this one.
Titanium chloride. So we have 4 chlorines, 4 times. Oh, you got the whole thing already? So just for those,
It's a
slackers.
lot slower.
Yeah. So 35.45, is that right?
Yeah.
Chlorine. So 4 times that amount. Okay. And then we have 1 titanium. And then how much does titanium weigh?
47.867. Oh.
That's awesome if she did. I'm like, man. Okay, so we got 4 times 35.45 plus 47.867. So you got 189.6. Okay, and we know the units are in grams per mole, right?
Question, do you use a mouse or your finger to write it? Or like up head?
I use my finger.
Oh, that's
no.
pretty lie. There's no way.
I do.
That's
That's
pretty
being
good.
a math.
Yeah.
Do you want to come and watch me?
It's hard, like, yeah. Okay, all right.
So,
Get back.
I use my mouse. I've had a lot of practice.
Your mouse.
The mouse pad, my finger on the mouse
Oh,
pad. Yeah.
that's a good question.
So, okay, so we know that that's grams per mole, right? So since we know that this is grams per mole, if I have kilograms per kilomole, yeah, so in other words, kilograms over kilomoles, right? Kilomole, right? Kilomole, yeah, kilomole, kilograms over kilomole. So that'll just be 1,000 grams over 1,000 moles, so the thousands are gonna cancel out. So they're equivalent. So in other words, the unit, as long as I keep that prefix, right? And I use kilograms per kilomoles, it's gonna be exactly the same value. Right? And then I could just, my grams per mole is gonna equal my kilograms per kilomole. And my milligrams per millimole will equal my, the same as well. So it doesn't matter as long as you're consistent about the prefix that you're using. Does that make sense? Because for instance, I know that a kilogram is 1,000, right? 1,000 grams. And I know that kilo prefix also means 1,000. So I have 1,000 over 1,000. What does that equal? 1. So as long as I keep the same prefix, right? The kilograms over kilomoles, it's going to equal the same value as my grams per mole. Does that make sense? Okay, and that's always going to be the case. That's whether you use micrograms. If I have micrograms per micromole, same case. If I have milligrams per millimole, same case. Okay, because the prefixes are on both top and bottom, so when they cancel each other out. Okay, so then I can just use kilograms per kilomole. So then I could say I have 189.67 kilograms per 1 kilomole. Okay, so then that allows me to get moles, right? And that is for titanium or chloride. Okay, so those units are going to cancel out, and then that means that I would be left with just moles, right? Kilomoles, right? So, but now I know I have the ratio of titanium or chloride to titanium or oxide, right? What is that ratio? It's 1 to 1, right? So then for every 1 mole, of titanium chloride, titanium chloride I can make 1 mole of titanium or oxide. Okay. So then the moles of titanium, or you can also use kilomoles. Kilomoles or kilomole, right? So then the kilomoles are going to cancel out. And I want kilograms, right? So then what is the molar mass of titanium or oxide? So we know that the titanium was 47.867. And then oxygen is what? There's 2 of them. So together it's 16 times 2, which is 32. All together, $79.867.
Yes.
Okay, so then, and that's kilograms per kilomole. So then we plug that in. So we want moles on the bottom, so 1 kilomole on the bottom. Titanium oxide. And then 79.897 kilograms. Is it 867? Oh, sorry. I'm just making sure you guys are on your toes, that's all. The titanium oxide. And so, and that's going to give me my kilograms of titanium oxide. Kevin, you're awfully quiet today. Usually can't get you to stop talking. What's going on? He said he seems pretty normal. Kevin.
Oh.
guys get? Okay. Well, you guys are expecting it to be so much harder, huh?
Yeah.
So always the very first step is the chemical equation, number one. And start off with what you're given. If you're given grams, kilograms, then all you want to do is use molar mass. If you're already given moles, then you're one step ahead of everybody else, right? Just, let's see. Everybody got this down? Give me a second. And so have you guys been doing the work on Chem 101 or active learning? I'm a man of habit, can't tell. Yeah? The drag and drop, you know? Well, that's all this is drag and drop. Get used to it.
It's not that bad, honestly.
Yes.
Like, the thing is, on active learning, it gives you an answer, so you just gotta figure out how to what goes where.
Yeah.
It gives it the answer.
It limits your options.
Yes.
Yeah, basically. But like if you're doing it wrong, you don't know.
Yes, so the drag and drop, it helps you set up how you should be doing your stochastic.
Yes. And then it'll tell you, it'll let you know you're going the wrong direction. It'll calculate.
Okay. So did that help?
Thank you.
No problem. Okay, I'm gonna clear it, and then we're gonna take a look at question number one. Then I want you guys to walk me through it. Okay. Question number one is a little different. So how is it a little different? It applies to molarity, and we know that molarity, the units for molarity is what? Moles per liter, right? So if I'm given liters, I can start with my given, which I am given, and I'm also given my molarity, right? Oh, I get a twofer out of this. So, and they tell me that I have excess gallium, right? So that means that's all I got, tons of it. I don't have to worry about it, right? So that's pretty good. So then if I have 2.6 liters, and you just told me that molarity means moles per liter, right? So then I can put my 1 point, carried away, ahead of myself, and that's HCl. And so then if I have 1.44, and that's moles, because you told me it means moles per liter per 1 liter of HCl. So then I can get my number of moles, right? So liters are going to cancel out. So now I have my ratio, right? Because what am I supposed to find? I need to find out how many grams of gallium chloride I'm making, right? So then my ratio of HCl to gallium chloride is 6 to 2. So for every 6 moles of HCl,
Oh, sorry.
I'm going to end up with 2 moles of gallium chloride. So then, now that I have 2 moles of gallium chloride, I can change, I can get my molar mass. What is the molar mass of gallium chloride? How would I calculate that? Okay, so I would use the periodic table. So that's 69. So 176 altogether.
Mhm.
6.0 what?
0.07.
Three. Together, and so that's going to be grams per mole. So then I can use that mass 76.073 on top.
It'll stay safe, it'll search. Later, like, that thing where-
I was just keeping you on your toes. What did you guys get? You guys get. How many sig figs did it be? 3 sig figs? Are you sure? 2 sig figs. So it should be 2 sig figs.
Yes. I should harvest them.
If we got that. Oh, okay, yeah.
Got you that?
Oh, no, it's too anyway. Sorry.
You guys are.